whatever Jimmy got.
Hopefully the weather's fair for these last few weeks so we can enjoy life.
I only have 3 lectures left. I wish we were. I'll be honest with you. I wish Tuesday was the last day of classes.
Monday is right. Yeah, we have next week and then we have Monday.
Yeah, that's it. That's it. Yeah, I would love one more day. Just one more day. But I think we'll get to molecular orbitals today. And I'll do diatomics on Tuesday and then polyatomics on Thursday.
I was gonna say something about that.
I don't know if I'm gonna do a couple. I think I will. I'll probably do a couple on next Thursday. Do diatomics
I
on
know
Tuesday.
you've always used Huckle usually.
Yeah. And then I gotta figure out what the problem set's gonna be for.
When it's going out.
Well, it'll go out. It'll go out Tuesday. And then it'll be due on the 7/38 or something.
Last day of exams is the 8th or
I think
9th,
it's the 7th, but I could be wrong.
somewhere around there.
Excuse me.
I believe the last few weeks in Abby's snow showing the class. You might still be burning, but
Yeah, I think she might be half dead. She's just trying to like conserve what energy she has for her class. So
Oh, no, he's not.
I don't know how to open these blinds. It's kind of dark and gloomy. Yeah, none of those works, but I'll try it. Maybe it's this one.
very scary. On the blackouts. I was not expecting more blinds. Right, so it's okay if you guys fall asleep, but if these are down, I'm gonna fall asleep.
I will fall asleep my last class. How I sit anyway, like the rest of the time goes on, I just have more. Everyone like their classes like that.
Okay, good afternoon, everybody. We have just 3 lectures left, which is the little unfortunate. That's my fault. It's just little extra, well, as you guys know, I go off on tangents sometimes. They always add up and they've added up to the point where I'm a lecture behind. So I'm gonna have to so what I'm gonna do with molecules is, I'm not gonna talk too much about the nitty-gritty theoretical details of how to construct molecules. And kind of skim over some of that nitty-gritty details. Instead, try to get to the real meat of the discussion. That's okay. For the first half of this lecture, I do want to talk very briefly about the way that we're going to tackle the problem of molecules. How do we calculate wave functions of molecules? How do we calculate energy levels? And we're going to talk about what we really care about, as we'll see, are orbitals. What are the orbitals of molecules, right? What do bonds look like in terms of their wave functions? And so I want to set the problem up in kind of a qualitative way. And then I'll give a sketch of how we're going to tackle this problem computationally. And I'm not going to go into too much detail about that, but just to give you a sense, and then we'll start for the rest of our semester. It's the other 2 lectures, kind of look at applications. Okay. So hopefully today we'll got to the point where we have an idea of what we're constructing for molecules, the problem that we need to solve for molecules. And then on Tuesday, we'll talk about diatomic molecules. Always go back to 2 atoms. And then on Thursday, we'll talk about examples of polyatomic molecules. I think that'll put us in a good position to at least get an understanding of the structure of molecules from a physical point of view. So let's think about where we've been. We've been talking about atoms for the last couple of weeks. And the nice thing about atoms is that we kind of have a good understanding of how they work. Hydrogen really gives us a good approximation for what an electron does when it orbits a nucleus. And I've discussed in the last couple of lectures about what happens when you add more electrons to your system, to your atom. And we see that by and large, things don't look that much different from hydrogen. The electrons in a valence, multiple electrons in a valence shell, will interact with each other. It does affect the energies. But the trends are very kind of straightforward. We talked about Hund's rules. We talked about how you fill electrons, the way they function, at least qualitatively in the atoms. And they're not too much different from hydrogen, right? Hydrogen provides us a lot of understanding. And that's really powerful because we can use our knowledge of hydrogen and bootstrap our way into molecules. And the way we're going to tackle molecules, there's many different ways to tackle molecules. We're going to tackle it from the perspective of taking 2 atoms and adding them together. Literally. We're going to have two hydrogen. We're going to learn first molecule we're going to look at is H2, hydrogen molecule. We have 2 atoms, hydrogen atoms, where the electrons are in the 1s orbitals. We're going to bring them together and see what happens. Right? We're going to add them together. That'll be our solution or our approach to a solution for the molecule. It's just an addition. We'll realize it's a little more complicated than that. But that will give us a really good framework for building molecules. And it's a very powerful way to do things. So what I want to talk about today, to begin with, is just to start thinking about this problem, right? Let's just set up hydrogen molecular hydrogen problem, right? Let's remember, every time we come up with a new problem, we do the same thing, right? We want to calculate the Hamiltonian for our system, right? We want to think about all the different potentials and kinetic energies of our system. And then we want to solve the Schrodinger equation for the wave functions and the energies. So let's do that, all right? Let's set up our Hamiltonian. Now, I'm not going to do this quantitatively, but rather I'm just going to tabulate in a qualitative way all of the forces and all of the interactions and all the energies in the hydrogen molecule. And I will identify a particular problematic point that we'll get, right? We'll construct it exactly the way we did with hydrogen, but now we have 2 hydrogen atoms with two electrons. So the first thing I want to do is let's set the problem up in space, right? Let's just draw everything out. All right, so we're going to start thinking about molecular hydrogen here. And of course, the first thing we should do is we got two protons, right? We have two hydrogen atoms. We're going to separate at some distance. So let's go ahead and draw those two protons as two nuclei. So we have a nuclei 1 and another nuclei over here, right? These are our hydrogen protons for our two atoms. Right, I'm going to label them HA and HB. These are the protons. And I'm going to separate them at a distance r. Right. Well, that's half of our particles. Of course, each hydrogen atom brings to the table an electron. Right, so there are two electrons floating around these protons at some distance. Let's go ahead and draw them. All right, we might have one electron here. We'll call this E1. And we have another electron, I'll put it at a different position, maybe over here, E2. And we can draw little vectors, little displacement vectors between all of these and measure all of the distances, right? So one distance that will be important will be the distance between the two electrons. I'll call R12. Right, there's that distance between them. Right, because of course we have to consider this because the electrons repel each other. But each electron is also attracted to the nuclei, right? So we're going to have a attractive term, or we're going to have a distance we're going to need to measure between the electron and its original nucleus. We'll call that R1A. Right? It's the distance between electron 1 and nucleus A. And then we're going to have another distance, R2B, right? Which measures the distance between second proton and the second electron. And then we're going to have the cross distances as well, because each electron is attracted to each proton, right? It's got two attractive forces. It's attracted to both. So we're going to have one that looks like this. That would be R1B. Right? And there's also this one along this axis, which is R2A. So it's not hard to see that this is all the possible coordinates for this system. We track the electrons relative to each other, protons and the electrons with respect to each other, and everything else. And the protons with respect. Okay, so these are all the coordinates of the hydrogen atom. But again, this is a scary thing because each of these coordinates is a function of three variables, r, theta, and phi, right? These are coordinates and spherical coordinates. Right? And we have many different coordinates we have to track. So our Hamiltonian is going to be a complicated set of variables. Right? Our wave function is going to be, ideally, what we would like is a wave function that explains the behavior of all of these together. And it's going to be a function of all of these coordinates. That's a pretty complicated problem. All right, but let's not worry about that so much. And let's think about how we can break down the energies of this system first. Right, so let's not worry about the wave function. Let's look at the Hamiltonian. That'll really tell us what the wave functions look like. All right, so what are the different forces that we feel in this system? All right, what are the different terms of the Hamiltonian? Or what are the terms of the molecular Hamiltonian for hydrogen? Well, just like we did with hydrogen, we just need to, right? We have to count all the kinetic energies and all the potential energies. Right? And we have 4 particles, right? So we're going to have 4 kinetic energies. So the first set of terms is going to be the kinetic energies of the nuclei. Right, this is the nuclear motion. They're going to be moving around with some kinetic energy. We also have the kinetic energy of the electrons. And let me color code this. Electronic. And that exhausts all of our kinetic energy. There's only 4 particles, so there's going to be 4 kinetic energies, right? We're going to sum up all the energies of all the little all the little particles moving separately from each other. Right, but we also have kind of a complicated set of potential terms, right? Because we have repulsions between the electrons, repulsions between the nuclei, and attractions between the nuclei and the electrons. Right? They're all repelling and attracting each other by some amount, which is a function of their distance. So we first have, we'll write it like this, the nuclear repulsion energy. And the potential for that is a function of R, big R, right? And that's going to be E squared over 4 pi epsilon naught R. Here, the charges of the protons are just 1, so there's no factor of a positive charge here. The positive charge is 1. But it's repulsive because, again, they're both positively charged. The nuclei are repelling each other. And of course, the electrons repel each other as well. The potential for that looks exactly the same. It's electrostatic, E squared over 4 pi epsilon naught R12. R12 is the distance between them. And then we have all the attractive terms, right? We have 4 coordinates that measure the forces between each nuclei and each electron. So there's going to be 4 terms for attraction between all the different combinations of the electrons and the nuclei. We can call that nuclear electron attraction. And these are all coordinates of what here I have it as R1A, R2B, and the other coordinates, the cross coordinates, R1B and R2A. Right, so each electron feels the attractive force to each of the protons. Right, and that's it. Right, so our Hamiltonian has 1 term, 2 terms, 3 terms, 4 terms, 8 terms in total. Right, so the Hamiltonian is going to be this really, really long operator that has a bunch of kinetic energies, right? H bar squared over 2 times the mass times the second derivative of the displacement, plus a bunch of attractive terms that look like 1 over the distance, right? The Coulomb terms, right? There's electrostatic potential. And there's 8 of them. Right? That's a lot of things to deal with. But here's the interesting thing. If we ignore the electronic repulsion term, right, which is the only thing that's really new here. Right? Think about if we separated these 2 atoms at really, really far distance, so the electrons are really far apart from each other. Right? This system looks a lot like 2 hydrogen atoms separate from each other. Okay, so they're each going to have, they still have kinetic energies, right? These are still terms that you'll have in the separate limit, at the distance, the limit where the atoms are very, very far apart, no bond occurs. These terms are still there. You still have a very, very small nuclear repulsion energy. And you also have very weak nuclear electron attraction, right? Because the electrons, E2 is still attracted to B, and E1 is still attracted to A, regardless of the distance between the nuclei. So what that means is that this Hamiltonian kind of looks like the Hamiltonian for atom A plus the Hamiltonian for atom B. But as we bring them together, the electrons will start to interact with each other. Right? And this term, this electronic repulsion energy term, will start to get big. Of course, also the nuclear one does too. Right? But we're going to make an assumption here that we've been making over and over again about this system, which is that the nuclei don't move compared to the electrons, right? The electrons buzz around the protons, so the nuclei, at a much faster speed, right? The kinetic energies of the electron are much larger than the kinetic energies of the nuclei. Right? So what we're going to do is make an approximation. This approximation I've introduced before. We're going to make what's called the Bohr-Oppenheimer approximation. Right now, again, I talked about this when we talked about vibrations, right? The elephant and the flies. Right? And we're going to approximate this, that we're going to assume that the nuclei move independently of the electrons. Right? Nuclear motion independent of electron motion. You saw Oppenheimer. Oppenheimer gets out of Germany with his PhD and he talks to Einstein for the first time, and he talked to a couple other people. And they're like, hey, that work you did with Bohr was really cool in your PhD. I really liked it. They mentioned it for like 30 seconds. This is it. This is Oppenheimer's PhD work, the Bohr-Oppenheimer approximation. This important distinction, or this approximation that we make, that basically enables us to solve the molecular problem. And what this means is that we can move the nuclei independently of the electrons. All right. So what we're going to do is this: we're going to make what's called the clamped nuclei approximation. Which is that we're going to fix nuclei at distance r. Right? We're just going to put them in a spot some distance apart from each other, and calculate the electronic energy or the electronic wave functions as a function of big R, the distance. All right, so what we're going to do, if we want to know how a molecule, the bond looks like at all positions, we're going to take the nuclei and step them. Right, we're going to move them to here, freeze them, and figure out what the electrons do. All right, what we call, we relax the electrons around the nuclei, calculate their energies and their behavior, step the nuclei again, calculate the electrons and how they behave when the nuclei are set to these distances, and do it again. Right? We're going to sweep over, right? And just clamp the nuclei and do the electronic problem separate. Right? What this does is it separates the physics of the nuclei from the physics of the electrons. So we don't have to, we can solve them separately. Right? We're going to separate the system into a nuclear part, which turns out to be very, very easy to do, and an electronic part, which is harder. It's always hard, but it makes it easier because we don't have to worry about the nuclei anymore. So what this means is that the Hamiltonian for our molecule has an electronic part and it has a nuclear part. And the wave functions for this system, so the total molecular wave function, is a product of a wave function that's a function of the positions of the atoms, or the electrons, sorry, R1A, R2A, R1B, R2B, and a wave function that's just a function of the nuclear coordinates. Right? We separate out everything. Okay. So we can solve the nuclear part easily because we fixed them. They're not moving, they have no kinetic energy. We fix them, so their kinetic energy goes to zero. Let me just scroll up really quickly, right? So if we've clamped the nuclei, when we calculate the energies, this part goes to zero because they have no kinetic energy. They're not moving. Okay, so this term goes away. And the only thing we need to calculate is how much energy the nuclei repel each other, right? That's the only thing dependent on their coordinate. Right, so that's really easy to do. We just calculate the charges of the two nuclei, which are 1 here, calculate the distance, and we get an energy out immediately. Right? It's just a number. Right? And we're going to do that at every single step. And so so we get rid of all the nuclei problem, we don't have to worry about it anymore. Fixed. Simplify the nuclear part. But now we have to solve this electronic part, which of course is a function of the coordinates of the electrons with respect to these fixed nuclei. And there are 4 coordinates because there are, again, 2 nuclei and 2 electrons. All right. So what I want to focus on in particular, right, this part right here is really easy to do. Right, and we've looked at these kinds of things when we talk about vibrations, for instance, we've looked at these nuclear wave functions because we calculate the energy of the molecule as a function of the bond length, right? We change R and we get an energy, right? We get a Morse potential. Right? So the energy of the nuclear part looks like a Morse potential. Right? So we already kind of know how that works. We just don't understand how do the electrons act at a function at a distance. That's the tough part. What do the electrons do? All right, so what we want to focus on is this electronic part in particular. Right, this is the thing that we need to solve. All right, these are the things that we care about. The nuclear part is like whatever. I mean, of course, it's important, but it's not really the key issue. Right, we can use the Morse potential to think about the nuclei. Right? The energy levels of the different nuclear positions are the vibrations. We've already done that. So now we got to think about the electrons. Now here's the problem. Let me just find my right note here real quick. And let's see, 67, page 66. Here, excellent. We'll just move these pages. Okay. So now let's look at this electronic Hamiltonian. Right? And the way that we can write this, let's go back to the idea of treating this system as 2 separate atoms that come together and interact. Okay, so the way we're going to write this is we're going to write it like this. We're going to separate it into parts where we have one for just the atom A. Right, so this is the energy of just atom A, 1 electron, 1 proton centered around A and HB, right? A Hamiltonian for B. And these 2 things are just the hydrogen atom Hamiltonians. Right, so we have this atomic contribution. And this will be the energy of the molecule if there's no interaction between the 2 atoms, right? If the atoms don't interact at all with each other, then the total energy of the system is just the energy of atom A and the energy of atom B. They're just hydrogens. Right? These have wave functions that are the 1s and the 2s orbitals, right? We talked about them for the last couple of weeks, right? These are just hydrogen atom orbitals, energies. And of course, they give you hydrogen wave functions. Right? So they each satisfy the Schrodinger equation. This is the position of electron 1. right? If you apply a Hamiltonian, you get the energy of that electron back, or that atom back, times the original wave function, right? And these energies are just the hydrogenic energies, right? These are the hydrogen orbitals. And these are the hydrogenic energies. This is just an example, right? And this is also true for B. Okay. So our problem at infinite distance is just two atoms added together. Very simple, right? But we're going to bring them together, and obviously the atoms have to interact with each other, right? Because they form a bond, right? We don't see hydrogen in the atmosphere or on Earth as H. We see it as H2. And we know for a fact they form a bond. So there has to be some interaction energy between them. That is attractive. Attractive, right? They have to come in and bind together. So there's going to be an additional term, a new term called HAB, right? The interaction term. And what this term is, what is it dependent on? Well, it's dependent on the interactions of, say, the electrons around B interacting with atom A, and atom A's electron interacting with atom B, and also the two electrons interacting with each other. And I want to focus in on that particular term, the one where the atoms, or sorry, the electrons are interacting with each other. This has a term that looks like what we call the hydrogen, or sorry, the electron-electron repulsion energy. So VEE, electron-electron repulsion, which is a function of the distance between the two electrons, which is E squared over 4 pi epsilon naught R12. And if we let the position of E1, the electron 1, be R1, and E2 equals R2. I'm just changing my coordinates a little bit. Then this equals E squared over 4 pi epsilon naught times the absolute value of the position of the electron 1. Sorry, let me call that 1. I apologize. Minus 2. All right, we just add the vectors together and get the difference between the two. All right, so let's think about the coordinates of this system a little bit. Okay, so this part of the Hamiltonian, the wave functions are only dependent on electron 1, right? Because it's just hydrogen A. The coordinates of this only depend on electron 2, R2, right? Because it's just hydrogen B. But this interaction term depends on both of them. Okay, so we have two terms that are independent of each other. They each interact, they just deal with one electron, right? Each of these are one electron terms. I'll write that. These are one electron. And this term on the right here is 2 electrons, right? It requires the coordinates of both electrons. Right, so when we add this term, our net wave function for the system is no longer going to be just A and B multiplied together. Rather, there's going to be the wave function is going to have some term that's dependent on the difference in the coordinates. Right, that should make sense, because if one electron is very far away from the other one, they don't repel each other very much. But if electron 2 is very close to electron 1, they repel each other. There's going to be an interaction term that has to be a function of both positions. And here's the problem. Now, I'm not going to prove this. It's not too hard to show. I'm not going to prove it, but here's the big problem. Is that if you take the commutator between the position of one of the electrons and then the position of both electrons together, this is not equal to 0. You cannot solve the Schrodinger equation simultaneously for both of these coordinates. So no wave function exists that allows us to define or to measure the electron positions
Just scroll up for one.
Yeah, of course. There you go. There's no wave function exists that allows us to measure electron positions and their relative distance simultaneously. So the moment that I introduce a system with 2 electrons, I no longer can solve the Schrodinger equation. Right? If I define my system in terms of its atoms, right, which means that I know R1 and R2, right, because these are defined with respect to the positions R1 and R2, each individual electrons into the atoms. And my wave functions are built around this assumption. And the moment I couple them together, I no longer can have a wave function that allows me to describe both of these things simultaneously. So I could maybe potentially solve something just for this, and I could solve something separately just for this, but not together. Okay, so I can either treat the system as a set of coupled electrons, which makes me lose basically all my information about the atoms. It's not going to be very helpful. Or I can treat the atoms as if they are not interacting. Okay? And that's a problem. Right? And this problem was identified immediately. People did solve the hydrogen atom, start thinking about atoms, and they're like, well, let's do quantum mechanics for molecules. It's about 1930, 1940. And they realized instantly that this problem arose, that the moment you add 2 electrons into a system, you can no longer create a wave function that is simultaneously defined for both parameters. Right? You can only have wave functions that are defined for 1 electron at a time. You can't have an exact 2 electron wave function. You can only have 1 electron wave functions. So that's a problem. Right? So we have to come up with some way. This is a problem that's very easy for us to solve, right? We've already solved it, right? We already know what the hydrogen wave functions and their energies are. Right? We've already solved this. Right? So is there a way that we could, for instance, solve this problem and then correct it very slightly for this interaction? Okay, so the idea is that this is the majority part of the energy, right? The 2 atoms, and that the repulsion, the interaction between them is very small, right? It's a small little perturbation. Maybe that'll work. Right? So we can assume that our system looks like 2 independent atoms, and their coupling, right, this interaction term is very small and only affects them very slightly, so that it's still reasonable to assume the system looks like 2 atoms, individual atoms. Okay? So the idea is that we're going to think this term is very, very small compared to these 2 terms. Because there's a little bit of a perturbation, right? I'd like to think about the ideal gas, right? The ideal gas, we treat all of our atoms as individual atoms. They don't interact. And then when we do the van der Waals approximation for the gas, we assume the interaction is very small, just a small correction. Right? So we've done this kind of approach before, and that's what we're going to do for our molecule. So of course, the question is, how do we measure that? Right? How do we take our atomic wave functions and measure or approximate the value of the interaction? Let's think about that a little bit. There's actually a really, really nice approach to this, it turns out. So what we're going to do is this. So our first idea is to solve the hydrogen atom problem separately first. solve HA plus HB first, right, which are two independent hydrogen atoms. That gives me an energy, we'll call it EA plus EB. That's the energy of this system. And the wave functions for this system is going to be the wave function of A for electron 1 times the wave function for atom B with coordinates for electron 2. Okay, and so our initial guess for the system is if we have two hydrogen atoms that are completely independent of each other, their energy summed together, and their wave function is just a product of the two. All right, so this is the what we call the free atom limit, or the, let's say this is like the non-interacting. All right, and so now we have this nice solution. We have these two atoms at some distance from each other. We know their energies exactly, right? They're Rydberg constant over n squared, right? It's just normal hydrogen atoms. And their wave functions, right? Remember, the hydrogen atoms in the ground state are 1s. Right? So these are just 1s orbitals for each of the atoms. I'll just write that here. Right? This is 1s1 orbital for each atom. Right? Just 1s. Very easy. Now, how do we calculate this interaction term? Right? How do we get EAB? Right? So what about the interaction term? Right? EAB.
Is it both those two terms, 1s1 orbital, the psi AR1 times?
Yeah, one is the 1s for the one atom and one is the 1s for the other one.
Oh, okay.
Yeah, they're each 1s orbitals. All right, so how do we calculate the interaction term? Well, let's just calculate the average of the repulsion. Right, so what if we instead calculated the way we always do, which is just to calculate an integral, right? If we calculate the integral of E squared over 4 pi epsilon naught times RA minus RB.
Is that non-interacting?
Yes. It's non-interacting. Right? So the way we're going to calculate that term is we're going to calculate the average of the repulsion between the two electrons, assuming that our system starts with two uninteracting atoms. This is the exact same approach we took on the midterm, right? We wanted to calculate the probability or the expectation value of the dipole taking my system from one state to another, 0 to 1, right? And without the interaction, which is the dipole in this case, in the midterm, the probability of going from 0 to 1 is 0, right? They're orthogonal. This is also true here. These are also orthogonal, or at least we think they are. They're orthogonal, so there's no probability that these two will interact, right? They're non-interacting. Right, so what we're going to do is we're going to bring them in a little bit, and we're going to calculate the average value of this interaction for our two atoms. So it's like this connective tissue that we're going to calculate an average for our two individual atoms. And if they're sufficiently far apart, this number should come to 0, close to 0. But the idea is that regardless of the distance, this number should be pretty small compared to the energies of the atoms. Right? So let's just make the assumption here is that EAB is much smaller than EA or EB. Very small. And in fact, that's pretty true. They tend to be on this order tends to be at most about 10%, if not less than. Usually it's about 1%. It's a small term. All right, but it's an important term. All right, and the way that we're going to calculate this, again, I'm not going to do the math. I'm just going to write the integral down. All right, it's an integral over three-dimensional space. of psi A star R1 times our operator, our repulsion operator, sorry, I called this R1 and R2. I apologize. R1 and R2 times psi B of R2 dr1 dr2. Actually, this is a two-dimensional network. All right, so what we're going to do is we're going to put our wave functions together and calculate the average value of the repulsion and integrate over all possible combinations or all possible positions of the two electrons. Right, we're just calculating an average. So so what we're doing now is simplifying our problem so that we start with two interacting atoms that we know exactly. And then instead of worrying about how their dynamics are affected by the individual positions of the electrons with respect to each other, we're just going to assume that it's an average effect. Right? That on average, the electrons will interact with each other. Sometimes they will, sometimes they won't. It depends on their distances on average. But we'll just integrate over all possible positions of the electrons over the atoms. And if this comes out to a number, it comes out to a number, and then we'll make an adjustment. Okay, so this is an average, right? So what we call this approximation, this is just a number. I'll just write that. Let me say that. This is just a number. It's just a number that comes out of here. And this is what's called mean field theory. And this is the fundamental kind of principle of how we solve complex chemical problems on a computer. So the assumption is what we're going to do is we're going to start with our starting materials, which are two atoms that don't interact. And we're going to bring them in closer and closer together and treat our system still as two atoms that are not interacting. And then as a function of their positions with respect to each other, we're just going to measure the average repulsion energy at those two positions of the atoms, and then just write the number down. Right? It's just going to make a small correction. All right, so what this means is that our wave function is still just a function of the two individual electrons moving with respect to each other. So there's no coordinate of our final wave function that's a function of both, R1 minus R2. There's no implicit coordinate. So each of the electrons act as if they're independent, but there's a small little correction of energy that we add because they may repel each other. Okay? And we just average that over the entire set of orientations for a given position of the atoms. And then we just calculate that as a function of the position. Just average overall. So what we're going to have to see is what does this do to our approximation, right? So as our atoms come together and the electrons start to repel each other, does that affect their wave functions? Right? Does it affect the energy levels of the atoms? Well, of course it does. Right? Because there's going to be some orientations of A and B, atoms A and B, where the electrons don't repel each other very much. But the atoms aren't very attracted to each other because they're far apart. And then there's going to be situations where the atoms are really close together and the electrons repel each other and the atoms repel each other, right? There's going to be a sweet spot. Right? There's going to be some orientation of all the electrons and all the protons, and all the nuclei rather, that's perfect. It's a Goldilocks position where everything wants to sit. Right? We're going to have to deal with those kinds of balances, right? We don't want things so close that everything repels, and we don't want things so far apart that they don't feel each other at all. Right? So there's going to be some sweet spot, and we're trying to calculate the average of that sweet spot. The average sweet spot. So there's an additional problem we have to deal with. So let's think about this for a second. So our initial wave function for our system is going to be psi1s comma a for the first electron times psi1s comma b for the second electron. The energy for this system is going to be EA plus EB plus the average value of the repulsion between the two electrons. We just looked at. But there's a problem with this. It's a very, very subtle problem. So you can, let me tell you, you can put two hydrogen atoms together. And in fact, I do it in my notes. I do it for the helium atom. This is the same approach that you would do for an atom with multiple electrons. You just have one nucleus instead. And you do this calculation. You can calculate all of this, assuming that each of the electrons in helium look like hydrogen 1s orbitals. For hydrogen, calculate the value of the integral. This integral is kind of annoying and somewhat convoluted, but I calculate it. And when you calculate the energy, say, of the helium energy of the ground state of helium or the ground state of hydrogen, you get the wrong answer. This is wrong. It's off. It gives you something close, but it's way off by quite a bit, maybe a factor of 2 or a factor of 3. So it turns out that this doesn't give you the right answer. And I'll give you an example. Let me find it. My notes. I know it's in here somewhere. Ah, yes. So for helium, for the energy, so this approximation gives you for the energy of helium in the 1s2 state is minus 108.8 eV. All right, but the experimental value is minus 79 eV. All right, so it's off by like 30–40%. All right, by making this assumption. All right, I go through this evaluation in my lecture notes. I'm not going to go through it today. I don't have time. But if you're interested in this derivation, I have it in my notes. This is for helium. Again, I'm not doing a molecule here. I'm just doing 2 electrons in an atom, but it's the same approach. So it gets it wrong by a little bit. It gets the right idea, but not quantitatively right. It's not to the level of quantitative precision that we're used to in this class and for quantum mechanics. This screams that we're doing something wrong. And it's a very, very subtle problem that took people a while to realize. It wasn't until about the 50s or so that people realized that what the issue was here. Very, very subtle problem. And it has to do with spin. Spin always throws us for a loop. And here spin is increased. The fact that electrons have spin plays a very, very critical role in our understanding of how atoms bond. All right, so here's the interesting thing. Remember that electrons, so here's an observation. And this should be obvious, but all electrons are identical. All right, because of the fact that I call one electron 1 and one electron 2 is completely meaningless because those 2 electrons are the same. I can't name them. They're identical. They're indistinguishable and identical. So let me say that, not only identical, but indistinguishable. So it's actually not really fair to call, say, one electron is 1 and one electron is 2, because they can swap, they can exchange. And there's nothing wrong with that, because they're identical and indistinguishable. So there's really no difference between electron 1 and electron 2. So there's actually two ways to write these wave functions. One is that you could say that electron 1 is around atom A, and electron 2 is around atom B. I put an equal sign here, and I'm going to put a gap because I need to put something else here. But there's nothing stopping us from writing it where we center electron 2 around atom A and electron 1 around atom B. There's no problem with that. This is called exchange, electron exchange. Right? And there's nothing stopping us from doing that. There's no energetic penalty for us exchanging electrons. Electrons do it all the time. You can even calculate the energy that you get from this. And in fact, hopefully what we'll see, I don't know if I'll have time to talk about these details. The reason why bonds are attractive, the reason why bonds actually exist is because electrons are allowed to exchange with each other and it actually stabilizes things. Electrons actually want to exchange with each other. They want to swap positions. The exchange energy is actually stabilizing. It's what causes the bond. I think maybe we'll talk about that on Tuesday. But here's the issue. What happens to my wave function when I swap the electrons? Okay, so let's think about that. These are both 1s orbitals. They look like spheres. Right? So this is an even function times an even function. So when I swap the coordinates, I should get it. I still have an even function, right? So you would think that when I swap the two electrons that I get a +1 sign, right? The idea would be that when you swap them, nothing happens to the wave function, right? The wave function's even upon exchange, right? That was the assumption that we made, that the electrons, when you exchange them, that nothing happens to the wave function, right? It's an even exchange. But it turns out that's not true. If you look at experiment, idea. I want to say that this is wrong, but this is our idea. Yeah, is that they're even upon exchange. But what experiment shows is that when you exchange two electrons between two atoms, you get a minus sign. Sign of the wave function switches. Strange. Now, how can that be? Because the functions, as I said, are even. So if you're swapping coordinates for even functions, nothing happens. But when I swap these coordinates, you find that in experiment, you get a negative sign on your wave function. Flip sign. And this is entirely due to the fact that electrons are fermions. They have half energy spectrum. You have to do this. This has to be true in order for the most important part about electrons to be valid, which is that only 2 electrons can exist per orbital, right? You can only have a spin up and a spin down electron in an orbital, right? So you can only have 1 electron per state, per position. And the only way to satisfy that is that you get this negative sign. I know that's kind of an odd consequence of the electron spin and Pauli exclusion. But this is a direct correlation, a consequence of that. And it's this, and there's a name for it, for this theorem. It comes from a very famous physicist named Paul Dirac, who actually derived it, called the spin statistics theorem. Which says that any wave function describing multiple fermions, so multiple electrons, multiple half-integer spins. So what are fermions? Things like protons, electrons, neutrons, basically everything in everything except for photons and chemistry, must be antisymmetric or odd upon exchange of electrons. On exchange. Has to be antisymmetric. Now, I won't go into the really, really nitty-gritty details why this is true. I go through derivation and argument in my notes about it. But it's not hard to show that the only valid way to represent two electrons in a system, in general, is that when you have your wave functions describing two different electrons or multiple electrons, that when you exchange the electrons, the sign of the wave function has to change, has to be antisymmetric. And I just wanted to say bosons, however, have the opposite. Bosons, which are particles with integer spin, including some atoms, or atoms that have integer spin, such as helium-4. Helium-4 must be symmetric or even upon exchange. Okay, so this approximation that I made, where I've just made a product of the two wave functions that's symmetric, this is not valid for electrons. This is why the numbers are all wrong. There's nothing wrong with the calculation or the approximation we make, right? Clamping the nuclei, assuming mean field theory that the average electron of repulsion is just an average, it's a small number that we correct for. That's all fine. The problem is that our assumption of what the molecular wave function looks like, which is a symmetric product of the two atoms, the two 1s orbitals, that is wrong. So the question is, how do we construct an antisymmetric combination of atomic orbitals? Right? What would be the proper way to write that? Okay, so now let's think about how to construct these. Right, so our new proper wave functions, proper antisymmetric wave functions, instead what we're going to write it like is going to be psi A R1, psi B R2, right? That's our original set. And we're going to subtract off the flip. So sorry, let me rewrite that. Sorry, psi A R2, psi B R1. Right, and it turns out, I'm assuming a couple of things here, but there's another combination that also works. I'm going to call this the negative one. We also have to normalize these. I haven't normalized them. There's also an equivalent solution that also satisfies the spin symmetry, spin statistics theorem, which would be a plus combination. which would be psi A, R1, psi B, R2, plus psi A, R2, psi B, R1. There's a symmetric, there are two possible combinations. We have a plus and a minus. So when we combine our two wave functions for our atoms, we start with two wave functions for two atoms. When we combine them and account for the anti-symmetry, we get two new wave functions out that are products of our atoms. So what we've done now is what we have are representations of our molecule's wave function as products or additions, combinations, if you will, of our atoms. So what this means is that, so we put in, the conclusion is that we put in, so the input are two atom wave functions. And our output are two molecule wave functions. Right? And the terms that we use for these, of course, these are called atomic orbitals, right? Remember, the thing that we've constructed our molecule from are just atomic orbitals. And what we get out are molecular orbitals. And the way that we're going to represent our molecule are by these anti-symmetrized products of our molecular or atomic orbitals. We've constructed molecular wave functions out of atomic wave functions. Right, so now that we have that, the question, of course, is now that we have two new wave functions for our molecule, good, I got 15 minutes left. Do their energies change? Right? Do the energies of what are the energies of our new molecular wave functions? Because they're now different. Right? What I've done is I've gone from two atoms and I've let them interact together by exchanging them through the repulsion term. They're exchanging because they're interacting, and I get two new wave functions out that are due to the fact that my two electrons are exchanging and interacting with each other. Right? These are interaction wave functions, right? These are interacting atoms. And the question is, the energies change. Again, how do the energies change? Well, so let's look at that. Let me just find my hydrogen energies really quickly. I want to do this with numbers just to be precise. Ah, beautiful. All right, so let's look at these molecular orbitals. Of H2. Okay, and so we like to draw these special diagrams for molecular orbitals. All right, so remember our atomic orbitals that we start with are 2x, 1s, 1 orbitals, right? They're two hydrogens that are both in the 1s1 state. All right, I'm going to draw a little diagram. All right, so my vertical axis is going to be energy. I'll make it a little broader. All right, and let's just put our energies of our two atom orbitals, what we start with here. So let's say I put an electron here. This is my H1s. All right, so I have an electron in my 1s orbital. And I have another electron here in my B atom 1s. Right, these are my atoms. Right, so let me just draw a little sketch of what these look like. And this is just a 1s orbital. Right, and what are the energies of these? Right, we should put these on a scale. Right, the energies of these, we'll do it just relative to ionization, minus 13.6 eV. Right, that's the energies of these. Let's do a different color so it's not. These are 13.6 eV. Right, and what do we get out? Right, we get out a two molecular orbitals. Our output should be that when these two atomic orbitals combine, we make two new orbitals where we've added or subtracted the atoms from each other. Right, so I'm just going to draw kind of a sketchy little dashed line here. Right, and so what we do is we're going to add we're going to create linear combinations of our atom orbitals, right? We're going to combine them, and we either get an additive sum of the two orbitals or a difference of the two orbitals. Okay, so let's do the sum together. Right, so if we add them together, these two orbitals, right, the wave functions look like this. They come together. They have the same sign, the same phase. They add constructively. Right, the two orbitals come together and they add constructively. So that means what happens is now you're going to make a more stable wave function. These electrons are now shared. They can exchange with each other in this additive sum, and they're allowed to share probability together and share space. This is a stabilizing effect. So our new molecular orbital, which is the sum, is going to be at lower energy. This is our new orbital, right, which looks kind of like the additive sum of our two orbitals. Right. I haven't given these names yet, but we can think of this as 1s plus 1s. Right? But we also get a negative combination, right, where we subtract one wave function from the other. Right? What is that going to look like? Well, that means that we're going to take a wave function of one of our atoms and add the negative version of the other one. So they're going to have opposite signs. They're going to destructively interfere, which means that the electrons in one are going to push away from the electrons in the other. They're going to push themselves apart. And by conservation of energy, right, if I bring in two orbitals at this energy, combine them, right, this is the total energy of my system. One of my orbitals goes down by this amount of energy. The other one must go up by the equal amount, right, for conservation of energy. If one orbital goes down in energy, the other one has to go up, because there's always a conserved amount of energy. So there's going to be a new sum. There's going to be a new molecular orbital at some higher energy, like that, where the orbitals are opposite phase or opposite sign. Right, they're going to be at different signs. This is 1s minus 1s. Right, that's going to be higher energy. Right, these are our molecular orbitals. So the question, of course, is where do the electrons go? Right, we have electrons initially in these two atomic orbitals. When we convert into our molecular orbitals, what are they going to fill? Well, they always fill the lowest energy orbital first. Right, so both of these electrons will be placed in this constructive addition of the two orbitals. Okay. Right, and what we can do now, of course, I don't know by how much these energies change, right? The question, of course, is I don't really know the magnitude of how much the energy changes. Because if the atoms don't interact at all, there's no interaction between the two atoms. The atoms don't combine at all, and there's no energy shifts for the molecular orbitals. They don't bond. Right? So there must be some way to measure that. Right? And of course, it's measured based on the interaction energy between the two atoms. Right? So this difference here, let me do it in a different color. Which is the same energy difference as this difference, is proportional to EAB over 2. I think it's EAB over 4. Let's just do roughly EAB. Let's say roughly EAB. Right, so the interaction term, as it gets bigger and bigger, increases the net bonding or the net interaction between the system. And because of these combinations of orbitals and the conservation of energy, as you interact two atoms, you form two orbitals. One's going to be a constructive addition that's stabilized by the interaction, and then you get another molecular orbital that's destabilized by the interaction. Right? And the sum of these equal to 0, as they should. Right? Energy is not, it cannot be created or destroyed, it's still conserved. The only energy that's being provided are the two atoms. That's the only sources of energy here. There's no way to lose it or gain it. But the electrons stabilize themselves because they're going to want to go into the orbital of the new wave function, the new orbital with the most stable level, right? The most stable energy, lowest energy. So our system bonds, right? We get a constructive addition of our atoms where now the electron that was once centered around atom A can be shared with B and vice versa, right? We have a sharing of electrons, right? It's a covalent bond. Right, this is a covalent bond. Right, we have two electrons and a bonding interaction. Right, that's a single bond. Right, this is a covalent single bond. Right, we have a fully paired, we have a fully filled, stabilized bonding orbital, where the electrons are equally shared between the two atoms. That's a single bond, right? We've just constructed a single bond, right? So the consequence of a bond is solely due to the fact that these electrons interact with each other. And there's going to be a sweet spot, right? There's going to be an arrangement of the orbitals where the electrons are interacting in such a way that it's stabilizing. And there's going to be an equivalent or a different approach, a different arrangement of them where they're repelling each other, right? And this is our constructive attraction between the electrons that forms a favorable bonding orbital. And then we form another molecular orbital where the atoms are repelled from each other, right? A repulsive state. Right? And we call these states, let me just write that out here, right? These are called anti-bonding states, right? Because they repel, they're repulsive states. Electrons that are centered around atom B push themselves away from atoms around A. They don't interact. And these are bonding states down here. This is a bonding orbital. That's an important term. Bonding and antibonding. And of course, you may wonder, what is this gap here? Well, we could figure that out. The ionization potential for H2, ground state, right, which is what we draw to the left here, is equal to minus 16.4 eV. Right, so this energy, right, that's the energy to remove an electron from this orbital. Right, so without the interaction, the electron takes 13.6 eV to remove. But now when you bond hydrogen with itself, it takes 16.4 eV to remove, right? So what does that mean? That means that this gap here is the difference of those two numbers. And then I want to write one more thing. The energy, the ionization potential for H2 plus, right? We've removed the first electron. What's the stabilization of the second electron in H2? It's also, oh, I'm sorry, I screwed these numbers up. This is minus 16.4 eV. This one is, sorry, I read the wrong number. It's close. It's minus 15.4. My God, this number has been measured to 12 significant digits, so I'll just give you a couple of them. 14.18 eV.
Is that 1?
1.8, yeah, 1.8 eV. And H2, so it takes 15 eV to remove the first electron from hydrogen molecule and 16 eV to remove the second one. So that means that 2H to 2P plus 2E minus, right? Full ionization of the hydrogen atoms. The enthalpy of this is 27.2 eV. And then for H2 plus E minus, that's the first ionization. Then 2P plus 2E minus, that's the second ionization. This takes 31.8 eV. So that means, therefore, the bonding interaction stabilizes the atoms or the electrons. By the difference.
That's 31.8.
Yeah.
for H2.
Yeah. I'll rewrite it. So when you calculate the difference of these two, that means that the electrons in the hydrogen atom are 4.6 eV more stable than they are in the two atoms separately. Right? It takes 27.2 eV to ionize two hydrogen atoms, but it takes 31.8 eV to ionize both electrons out of the hydrogen molecule. Okay? So that means the bond, this gap right here, in total is 4.6 eV. Right? That's the bond strength. Right? This is the bond energy of hydrogen. Bond energy of hydrogen. Right? So this number here is minus 4. I'll write it. All right, I'll go ahead and erase this EAB thing here. This is minus 4.6 eV. Well, divided by 2 because there's 2 electrons. I apologize. It's 2.3. There's 2 electrons. I got to divide by the number of electrons, and this is plus 2.3 eV. Okay, so this is okay. I'm done for just one more sentence to say because we're out of time. This is the construction we're going to move forward with. Right? Take 2 atoms and assume that the amount of energy change they have when they interact is quite small. Measure the average interaction, and then combine the 2 orbitals together, the atomic orbitals together, into molecular orbitals. And depending on how those orbitals overlap, how they interact, we will either create pairs of stabilized and destabilized molecular orbitals. And this will teach us exactly what the molecules look like themselves. Okay, so we'll look at this more carefully next week. All right, have a good one, guys. Have a lovely weekend. I'll have the next homework, the final homework out probably Tuesday before class.
You're doing office hours tomorrow, right?
Upstairs.
Yep. From 11:30 to 1:30.
I will be there. I should be there at 11.
Okay. My water.
Yeah, I'll see you upstairs.
Your office hours are still in Maxie?
Are you doing yours in Maxi today?
Yeah.
Oh, okay.
I'm gonna have to nap. Thank you.
Thank you. Have a good one.